Theory of columns, short versus long. Welcome to Blueprint to Reality, where we break down complex engineering concepts into easy-to-understand lessons. In this episode, we will explore the theory of columns, focusing on the differences between short and long columns, an important consideration in structural design. What is a column? A column is a vertical structural element designed to support loads, typically compressive forces. Columns are found in almost every type of building or structure, from bridges to high-rise buildings. They are designed to carry the weight of the structure above and transfer that load down to the foundation. Short versus long columns. The key distinction in column theory lies in whether a column is considered short or long. This classification depends on the column's height and dimensions relative to its material and cross-sectional shape. 1. Short columns. A column is considered short when its height is small compared to its cross-sectional dimensions. In this case, the column primarily behaves like a simple compressive element. The load applied to the column causes it to shorten proportionally, without any significant bending or buckling. 2. Long columns. A column is considered long when its height is large compared to its cross-sectional dimensions. In this case, the column is more likely to buckle under load rather than simply compress. The buckling behavior becomes critical in the design and analysis of long columns. Why does column length matter? The length of a column is crucial because it determines how the column will behave under compressive load. Short columns, because of their relatively small height, can carry more load without the risk of buckling. However, long columns are more prone to instability and buckling, which can lead to catastrophic failure if not designed properly. The relationship between the column's height and its resistance to buckling is key in understanding why column length matters. What affects the buckling of long columns? Several factors affect the buckling of long columns. 1. Material properties. Stronger materials with higher Young's modulus will resist buckling better. 2. Cross-sectional shape. Columns with larger moments of inertia, such as wide or deep sections, will be less prone to buckling. 3. End conditions. The way the column is supported at both ends plays a significant role. Fixed supports increase the column's ability to resist buckling, while free or pin supports make buckling more likely. 4. Load type. The application of a compressive load at the center of the column can cause buckling to occur more easily in long columns. Real-world applications. The difference between short and long columns is critical in the design of structural elements. For example, in a high-rise building, columns will typically be long and subjected to high compressive loads. In contrast, short columns, like those found in foundations or smaller structures, are more robust and less likely to buckle, allowing engineers to use them in situations where load-bearing capacity is the primary concern, without worrying about buckling failure. Conclusion. In summary, understanding the theory of columns, specifically the difference between short and long columns, is crucial for structural design. While short columns primarily carry compressive loads without the risk of buckling, long columns require careful consideration of their height, material properties, and support conditions to avoid buckling failure. Thank you for tuning in to Blueprint to Reality. If you found this explanation helpful, don't forget to like, share, and subscribe for more civil engineering insights. See you in the next episode. Strength of soil. What it means. Welcome to Blueprint to Reality, where we delve into the fundamentals of civil and structural engineering. In today's episode, we're going to explore the shear strength of soil. What it means. Understanding shear strength is crucial for foundation design, slope stability, and overall soil performance under load. Let's break down this concept and see why it's so important in construction. What is shear strength of soil? Shear strength of soil refers to the maximum stress that soil can withstand before failing in shear. It is the resistance of soil to sliding or deforming under an applied load. When soil is subjected to shear stress, the soil particles try to move past each other, and the shear strength determines whether they will resist or slip. Why is shear strength important? Shear strength is vital in several engineering applications because foundation design helps determine the appropriate type and size of foundations to prevent failure. Slope stability, essential for assessing the stability of slopes, embankments, and excavations. Earthworks, affects the design of retaining walls and soil structure interaction. Factors influencing shear strength. Several factors affect the shear strength of soil, including 1. Soil type. Different soils have different shear strengths, depending on their texture and composition. Clay, fine-grained and cohesive, with high shear strength when dry, but low shear strength when wet. Sandy soils, non-cohesive and provide resistance primarily through interparticle friction. Gravel, coarse-grained soil with higher shear strength due to particle interlock. 2. Moisture content. Moisture significantly impacts shear strength. Saturated soils. Excess water reduces friction between particles, decreasing shear strength. Dry soils tend to have higher shear strength as particles are more cohesive. 3. Soil density. The density or compaction of the soil affects the contact between particles. Well-compacted soils tend to have higher shear strength because the particles are tightly packed. 4. Consolidation. As soils consolidate under pressure, they become stronger. Consolidation expels pore water, increasing the interparticle friction and improving shear strength. How is shear strength measured? Shear strength is determined through laboratory and field tests that measure the force required to shear a soil sample or the force required to cause failure in the field. 1. Direct shear test. In the direct shear test, a soil sample is placed in a shear box and subjected to a horizontal force. The test measures the amount of force needed to cause sliding between soil layers. This test provides key parameters such as cohesion, c. the inherent strength of the soil particles. Angle of internal friction, phi. the frictional resistance between soil particles. 2. Triaxial shear test. The triaxial test subjects a soil sample to 3 different stresses: vertical, horizontal, and confining pressure. This test simulates more realistic conditions and is used for determining the shear strength under varying stresses. 3. Unconsolidated undrained UU test. This test is used for fine-grained soils, particularly clays, to determine their shear strength before they have had a chance to consolidate. It provides quick results, often used in time-sensitive projects. Shear strength and geotechnical engineering design. Shear strength plays a critical role in the design and stability of many engineering structures. 1. Foundation design. For deep foundations like piles or drilled shafts, shear strength determines the load-bearing capacity of the soil. Shallow foundations rely on shear strength to ensure that they don't experience excessive settlement or failure. 2. Slope stability. The shear strength of soil is crucial for assessing the stability of slopes, embankments, and excavations. A lack of shear strength in soils can lead to landslides or slope failure, which can be catastrophic in infrastructure projects. 3. Retaining walls. Shear strength is critical for the design of retaining walls, as the wall must resist the lateral pressure exerted by the soil behind it. Proper analysis ensures that the wall won't slip or topple under load. Real-world examples of shear strength in action. 1. Landslides. The 2008 Sichuan earthquake in China caused widespread landslides, where the shear strength of the saturated soils was compromised by the intense shaking. Many of the landslides occurred in steep terrains with loose soils. 2. Design of highways. When constructing highways over soft soil, engineers must carefully assess the shear strength of the ground. In some cases, the soil is reinforced using geosynthetics or other materials to ensure the stability of the road and prevent shifting or sinking. Conclusion. The shear strength of soil is a fundamental concept that engineers use to predict how soil will behave under different loading conditions. It influences everything from foundation design to slope stability, and its accurate measurement is crucial to the success of construction projects. Thank you for joining us on Blueprint to Reality. If you found this video helpful, please like, share, and subscribe for more in-depth insights into civil and structural engineering. See you in the next episode.